We're very happy to have Professor Dunkley here visiting us from Princeton. If you have read anything about the cosmic microwave background radiation over the last 20 years, Professor Dunkley has been an intimate part of it. She was on the WMAP collaboration, she was on the Lambda collaboration, she's on the ACT collaboration, she's on the Simons Observatory collaboration, and the CMBS4 exists as a real collaboration yet. Sorry about that. So she was a PhD at Oxford before going to Princeton to do a postdoc, but of course the people at Oxford knew how great she was, so they dragged her back to Oxford, but then the people at Princeton knew that she was great, so they dragged her back to Princeton, where she is currently. She has a host of many prizes. She's won the Gruber Prize twice, both as members of the WMAP team and the Plunk team. She got the Breakthrough Prize, a member of the WMAP team. She got the New Horizons Prize basically on her own. And something I did not know, but she is an officer of the Order of the British Empire, which I think is maybe the first officer of the Order of the British Empire we have had, which is why she's especially qualified to talk about what she's talking about today. So, please.
Thank you.
I think it's the official of the most excellent order of the British Empire.
That wasn't on the CT, actually.
Well, thank you very much. Well, thank you very much for the kind introduction. Yeah, it's super nice to be here and to have met some of you already during the day and to talk about this. Yeah, so I really I want to describe to you like the big questions I have in cosmology, which many of us have, and one of the big this big question I have that many of us have is is kind of a simple one. It's the big one, which is, you know, what is the model that best describes our universe? And it does. We've had now this model for more than 20 years, and it's called Lambda CDM, and it's been in place, and it's really not broken yet. I want to talk through that and how we might be looking for where it could be going wrong and how we can find what's going on with it. Okay, so what is this model? It tells us that our universe is geometrically flat. So light travels in parallel lines through it. It's not curved, it's not open and closed, it's flat. And its contents are regular matter that we're all made of, as well as some new invisible form of dark matter that we haven't yet identified, and apparently a cosmological constant. So the idea that the energy itself, space itself has an energy. If you take a box of empty space, it's got an energy. It's got this, you know, Einstein's cosmological constant. And it has really simple initial conditions that I will say more about, which is how the universe was shuffled around to begin with to end up producing what we see today. And this model matches this just enormous array of astronomical data that many people here work intensely on. And that data has measured the evolution of the universe over billions of years, and over very large different scales with different probes. And really anything we throw at it, almost everything, seems to work. Now, sort of the pursuit of this is when we try and kind of characterize this model, what many of us do is try and estimate its parameters. And I'll say more about this. So its ingredients and its initial conditions. I will say this partly for one of someone in the audience's benefit, that the values of these numbers that we measure, we talk a lot about in this field. What is the value of all these different quantities that describe this model? Those are not actually very interesting. Okay. The numbers, we can measure them, and we really don't care so much what the number is. We want to make sure that the numbers are consistently measured from different probes. And so if you can measure them precisely and accurately, both of those things, we can actually then try and ask whether the model is sufficient, because we can say, do we get the same ingredients and initial conditions from this data and this data and this data? Because if they don't agree, the model is wrong. And so the better you can measure them, the better you can determine whether it's the correct thing. Okay, so Neil introduced me. The probe that I use the most is the cosmic microwave background. So this is light that we're receiving now, that has been traveling to us since the universe was 400,000 years old, and at a temperature of about 3,000 Kelvin. So the universe started off incredibly hot, much hotter than that, 14 billion years ago, and it's been cooling and expanding ever since then. So it's been growing and growing and growing, and as the universe grows, it cools down, and the universe cooled down enough at 400,000 years, when it reached a temperature of about 3,000 Kelvin, that this critical thing happened, which was that the universe could turn from a soup of ionized particles, I think was around at the time, so ionized hydrogen and helium atoms, this soup of hydrogen, helium atoms and photons, and also we think this mysterious dark matter, it switched from being an ionized plasma to being neutral. So atoms could become neutral, hydrogen and helium could form atoms, and light that was created, and we don't exactly know the mechanism, in the very early universe, was then free to travel through space and to propagate through space forevermore until it reaches us. Some of it's reaching us here today. And that light set off from all places at that particular epoch, when the universe is 400,000 years old, traveled out, and again, we're just gathering some of it that happens to be reaching us here on Earth now today. And it's measured to be this very perfect, most perfect black body that of radiation that we see in nature. So this characterizes the intensity of this light as a function of its wavelength. It's this black body distribution that peaks today at around 1 millimeter in wavelength. So this is light that stretched its wavelength as it's traveled through space for nearly 14 billion years. And it stretched its wavelength all the way into the millimeter regime. So it's called the cosmic microwave background because it's millimeter length. And we measure it typically, the data that I'm using right now, typically we measure light that's about 2 millimeters in wavelength, is the light we see. And again, it's this very perfect black body because it's capturing the universe as it was when the universe was in perfect thermal equilibrium at the time it formed. And we see it as this distribution. Okay, so I want to just show you a couple of pictures of, because it's where I now work in Princeton, of the first experiment designed to measure the CMB at the top, okay, which is an experiment on the roof of the geology building, geophysics building actually in Princeton, by Bob Dickey's group. Here on the roof, my office is now kind of opposite the road here, and this is a zoom in on it, which is that in the 60s, the first experiment designed to actually look for this radiation. As it's now become well known, this experiment was scooped by this one, the horn antenna in Holmdel, New Jersey, by Arno Penzias and Bob Wilson, who weren't looking for the CMB, but they found it anyway as noise in their instrument. But then soon enough, Bob Dickey and his group with this experiment then went to detect it as well back in the 60s. This radiation was seen and then mapped over the sky to give on the surface a rather boring image. Okay, I like to have a reminder of this image because what it's showing you is the temperature of this CMB light on the sky. So the image of the CMB light on the sky. I'll show you a more interesting one in a moment, but the mean temperature is all the same temperature. Today, it's 2.7 Kelvin. The temperature has dropped by a factor of 1,000 because the universe has expanded 1,000 times in all directions since it set off. So the universe was 1,000 times smaller in each direction, and the temperature is 1,000 times larger when it set off. And it's the same temperature on average around us in every direction, which gives some indication that, like, back then the universe was really very boring and featureless because it was sort of capturing the temperature of the light really captures the conditions of the universe in different places, and it's saying that the universe is incredibly homogeneous, very smooth.
The image you showed, just a question occurred to me. probably obvious, but why is Penzias and Wilson's apparatus so much larger? Is it because they were looking for longer wavelengths?
Yeah, larger wavelengths. Yeah,
Okay.
because they were looking for other stuff. They were looking at the galaxy. So they were looking for more radio. And so if you look, yeah, they weren't looking for this, and they were looking for radio emission, and so they were just picking a different wavelength. But you can measure this at different wavelengths.
They just had enough sensitivity.
Yeah.
To see it.
That's right. Yeah. Okay, but if you zoom in on this, so what happened, and again, I'll step through, I'll jump 20 years in a minute. If you zoom in on that image and you take away the mean and also take away actually the dipole from the fact that we're moving, you see this. And this was the first indication that there are irregularities in the temperature of that light. But the color scale here is now like about 20 microkelvin in scale. This red band is not the CMB. It's actually light coming from the Milky Way that we sit in. So we sit in the Milky Way looking out, and the Milky Way itself emits light in the millimeter range as well. And so that's actually kind of in the way when we see it. But these blobs in the back are true features, irregularities in the temperature of the light. And I'll say more in a minute about what they're tracing. This was an incredible discovery, in the 1990s, because this was saying we are seeing, the seeds of cosmic structure that we now experience today in our universe. But it's now been measured to much greater detail through also past the WMAP satellite and now to the Planck satellite in the 2010s. This image, which shows the temperature fluctuations of that light, has now been mapped out to much greater detail and higher resolution. And so what you see here is kind of this latest all-sky image from the Planck satellite, where that red band has been removed artificially. It's still there. If you look at any image of the sky that the Planck satellite sees, it sees the red band of light from the galaxy, but you artificially remove it to try and see what's behind. So when you see that, it's been like cleaned of the galaxy band. And what you see is that again the scale of this is only tens of microkelvin. So the fluctuations are 1 part in 100,000 around a mean. They're really tiny hot spots and cold spots. And really, what this is more or less tracking is the density of the plasma back at 400,000 years. And so what we're seeing is that this soup of particles wasn't completely regular. It had slight over and under densities of order 1 part in 100,000 back at 400,000 years. And they are incredibly important because they're the things that then form us later, right? You need to have over and under densities at some point in the past if you're going to create cosmic structures today. We are a very overdense region here in the universe. If we didn't have irregularities back at the early times, we would never have them now. You have to have them so that where you have an overdense region, gravity will then start to pull more matter together, more hydrogen and helium atoms together over time until in the first millions and billions of years, you form galaxies and you form stars gradually. But this is the earliest snapshot that we can see where these blobs just track the density of the plasma back then. Again, the tiny overdense regions will eventually form galaxies. And the reason we love it, we sort of rave about how great this is for understanding like the Lambda CDM model, is that all the physics is basically linear at this point. These fluctuations are so tiny that the departure from a uniform density is tiny. It's again 1 part in 100,000. So we can follow the physics of those very well because they're not non-linear collapsed structures. They're very tiny. Okay, and so what do we do with it? We typically measure the power spectrum of that image. So I just want to walk through that briefly. So you take that image and you break it up into successively smaller and smaller scales, right? You start with, we decompose it in spherical harmonics, but think of it as like, large scales down to smaller scales as you step across this axis. Okay, you go from size angular scale along here, and you measure the variance or the power spectrum, or very broadly, the amount of bumpiness. How bumpy is that map as a function of scale, or what is the power spectrum as a function of scale? And what we get out is this red curve, these red points, which follow this very featureful pattern. And this green curve is the theoretical prediction of our favorite Lambda CDM model, which goes through the data points perfectly well, kind of remarkably well, that there is in fact a model that even fits this kind of quite featureful data.
When you say prediction, you mean fit, right?
Sorry.
Yeah.
I'm sorry. Yes. Yeah, absolutely. And I'll say later. Yeah, good. So here, yeah, absolutely. So in this case, good. I fixed, what we've done is search through all the different possible ingredients and initial conditions of this model until you find the one that best fits. And this would be the model for the best fitting model. Yes, you're allowed to change all of its parameters until you find the ones that goes through. And so what we do is, yeah, you can say, here's a universe. I'm going to predict this curve. I'm going to modify it until I find this one that works.
How many parameters?
6. And I'll show you what they are in a moment. This is also done, so Planck also measured the polarization of the light, not just the intensity, the temperature, but also its polarization. And so they also use that statistic to do this. Okay,
but I actually think this is a prediction in the sense that the space of possible predictions is very small relative to the number of degrees of freedom in the data.
Yeah, that's right. And so what, and the physics of what we're seeing, and I'll show this a bit more, is that this shape that we see is we think we had extremely simple initial conditions going in, which is basically you put in these perturbations, you perturb the universe at very early times, and then roughly the reason you see these bumps and wiggles is that when you have an overdensity in a photon baryon plasma, an ionized one, where the photons are scattering off the electrons, you have an overdensity, but you have the pressure of the photons pushing away from that, and so so an overdensity will source a sound wave that will travel through the plasma. And that will happen wherever you have these overdensities, and you'll have these sound waves propagating through this plasma. And they'll propagate until the universe suddenly becomes neutral, and then you'll capture what they look like then. And so some particular angular scales or length scales on the sky happen to correspond to length scales. This first one corresponds to a length scale that's kind of undergone like half an acoustic oscillation or half its oscillation of a sound wave between like the time of the beginning of the universe and the time the CMB forms. So so we're basically capturing these propagated sound waves that have all these features. So yeah, just coming back to what are they? So we do now have this pie chart, right, of what is the universe made of? So 3 of the parameters are ingredient parameters and expansion rate parameters. I said it's, so we have basically about 5% today of the universe is in regular matter, about 25% is in dark matter, and about 70% is in, it's called here the dark energy, but it's in the simplest model, it's just lambda, it's this cosmological constant, a vacuum energy. And that's the energy density today. I think it's quite helpful to remember that's not always the way it was. In the past, when the CMB formed, the pie chart would look more like this, where the vacuum energy is just like a negligible amount. This isn't there. And you actually have a much larger contribution from neutrinos and photons back then because they were relativistic and their radiation density was the density was more dominant. Okay, so 3 of the numbers characterize how much, the relative fractions of these 3 things, but they have to add up to 1, and also the expansion rate of the universe goes into that as well. And this model also assumes that there are photons, there are the CMB photons, and that there are 3 light neutrino species, and that's it. And what I think really Planck has done, built on WMAP's work in this field, where we've got to in the last 20 years, so we haven't found a real problem yet, at the moment, but we have really limited the possibilities of what else it could be. Okay, so we've looked at, there's no sign of any extra light particles. If we characterize the number of light particle species that could be neutrinos or something else, it's 3 plus or minus 0.2. There's little room. There is some room in there for something that's not a neutrino that's contributing, but it's much less room than even a few years ago. There's not yet a sign of non-zero neutrino mass. That's rather well constrained. Come back to this as well from the data. There's no departure we see from flatness, and this is not just in the CMB, but comes from the combination with the Boss galaxy distributions. This density and curvature is less than is measured to be extremely close to zero. And there's no yet departure from a cosmological constant. This W naught characterizes the equation of state of that dark energy, and -1 basically is what we'd expect if it's a vacuum energy, and it's that to within a few percent.
Is it really measured at that level?
Yeah, with the supernova data. So this is if it's a constant. If you assume it's a constant. If you assume it can change over the
That's 1 sigma from supernova?
Yeah, from the combination of supernova, BAO, and CMB data.
Does it assume it's greater than or equal to -1? Because for a while it was the central value. If you didn't assume that, it was below -1.
I don't think that is, but of course, if you allow W8, if you allow 2 parameters to vary, then it does want to move away from that. But I think that's for sorry, I was trying to simplify my slide. I should have left it on. I think this is from the Pantheon, latest Pantheon Plus supernova sample combined with other data. So
This is not a parameter of omega 6.
No, yeah, sorry. I'm sorry, I should have explained that. Sorry. Yeah, the parameters in the 6 are the 3 numbers that describe the density of basically those 3 things. Then what we can go and do is see if we did any of these, and we don't, right? So we don't need anything like of this list. We don't need to have geometry in there. We don't need a dark energy equation state. We don't need a neutrino mass yet. We don't need a number of neutrino particles.
So these are 3 extra parameters, but that you use from other measurements.
Yeah, I haven't got to there's 3 here. There's 3 on my next slide. Or there's actually there's 2 more. Okay.
And so in this bounds, you use 1 extra parameter at a time, right? So
yes, obviously, if you do a few of them at once, you can go a little bit further. Yeah, absolutely. Yeah. Okay, so 2 more of them. 2 more of the 6 are the initial conditions of the universe. Okay, what does that mean? Let me show you. So we can describe. So this little cartoon describes like the density of space, delta rho, the overdensity of space. So delta rho over rho, for example, the overdensities as a function of spatial extent. So you can imagine like characterizing a perturbed density field, 1D, as like a sum of long wavelength fluctuations and short wavelength fluctuations and everything in between. You can think of the Fourier space decomposition. And we think that the initial power spectrum of these fluctuations, so the variance in these kind of perturbations, is a function of wave number, K, where this is a megaparsec is about 3 million light years. So these are kind of hundreds of millions of light years scales, perturbations. We think they can be described by a power law. Okay, so this data is from Planck checking that that's a good approximation. But the model itself just has these 2 variables, which is the slope of this power law and the amplitude at a given pivot scale. Right? It's saying it's just a straight line. Okay, and what this is almost scale invariant fluctuations, where you have so it doesn't matter what scale we're looking at. We have almost the same variance coming at different scales. And that's consistent, it's compatible with having been generated during inflation in the earliest moments of the universe. So it's rapidly expanding, exponentially expanding space early on. And again, we see that the model has these 2 numbers, but one can check whether you see any departures from that. Do you see a departure from a power law? Do you see a departure from actually, we assume that these fluctuations are adiabatic, which means all the fluids follow each other in the early universe. More baryon, where you have an overdensity of baryons, you have dark matter, photons, neutrinos, all in the same place, which doesn't have to be true. You could have one go up, one go down. You don't have to have it all be the same. But then being adiabatic, which means following each other, is what you'd expect from inflation. And we don't yet see any signs of tensor perturbations in the early universe, so things that would propagate as gravitational waves, which again you might expect from a number of inflation models. We just don't see that yet. So you have the two initial conditions, you have 3 ingredients, and you have this one kind of extra parameter, which is when the universe reionized, when the first stars formed. And of course, that's more of an astrophysical observation, is when did the first stars form, but it scatters the CMB light and changes its amplitude. And so we sort of care about that as an extra parameter from the cosmological side. Of course, it's very interesting astrophysically too. We sort of carry it as a, in some sense, a nuisance parameter, in another sense, a very interesting parameter. Okay. So really Planck, I think, would say this, the success maybe of the last, in the last, decade from Planck is that we haven't, there isn't, we've tested so many things and there isn't a model that does better yet. But it's also, we can expect Lambda CDM to fail, or we can hope, I think, it will fail, because its fundamental ingredients are unknown to us. We don't know what the CDM is, we don't know what it's dark matter, we don't yet know what this ingredient is. Is it a new particle? Many people here work on this intensely. We don't yet know what lambda is. Is it really a vacuum energy? And if so, why is it the size it has? It's not got the same size, not got the size that we would necessarily predict from theories. And we don't know the physics of what produces initial fluctuations. Even though we have this idea that maybe it's inflation, we don't really understand fully the physics of it. And so I think many of us, we either expect or hope it to fail, because if it doesn't fail, we sort of probably haven't learned about those things, and that would be a sort of sadness, I think. So we kind of push on it and see, can we find it? Can we find where it's not working, to learn something more deeply about this model that does so well, but is sort of not fully satisfactory. So let me highlight 2 of the places where it possibly cracks are occurring, where we can push on. I think we should also push on other things too. One is that if you take the model that fits the CMB, then the expectation for how fast the universe should be growing today is 5 sigma lower than measured directly from galaxies. So the simplest way to measure the expansion rate of the universe is to measure how fast galaxies are moving away from us, or appear to move away from us, measuring the distances in redshifts. And if you do that using one sample of galaxies, or one way to calibrate the distances to galaxies, you get this H0, this expansion rate of the universe, that's up here, 73 or so, in its units, kilometers per second per megaparsec. And it's 5 sigma different from the prediction of the Lambda CDM model down here. Now, if this really holds up to be genuinely discrepant at that level, then we're already seeing Lambda CDM not working. Okay, you can't have those two be different within the one model. This is the prediction, and I'll come back to this later. There is another data set out there that doesn't disagree significantly. This is another measurement, another way to measure the expansion rate, and it's not as different from the one we predict from this model. So, and I will come back to this point. Okay, so I call it a curiosity rather than a definite problem. And the second one that I want to mention is that the expectation of how clumpy matter in the universe should now be is larger. Up here, this measure of clumpiness that I will begin to return to, is larger than has been measured directly by looking at how light is gravitationally bent around galaxies. And I'll show you how we do that. But so we sort of have this, again, this slight difference, and this is from 3 different galaxy surveys where they're measuring a lower value than is predicted from this model. So if any of these things were to really be definitely different, then you'd say Lambda CDM is not enough. You need something else. You have to put something else in. So that's why we try and push on it. So how are we trying to learn more? I love the CMB. I love it's combining other things, but it's sort of such a richness of data. We have been using this. We've been working in the Atacama Desert with teams of colleagues who've spent years working on this site. Back there is the ALMA telescope. It's up in the north of Chile, near the Bolivian border in the Atacama Desert. And we've been using this telescope pictured here, the Atacama Cosmology Telescope, where the goal is basically to go to higher resolution in the CMB and to better measure its polarization as ways of, again, pushing on how can we learn more, how can we test more. So this is a picture looking into it. It's a 6-meter telescope made of aluminium because we're measuring in the millimeter, so you don't need a glass mirror. You have an aluminium mirror to reflect the CMB photons, and it's shielded by this ground screen to stop stray light from the ground coming in, and it's at 5,000 meters elevation. It's actually not there anymore. It got taken down a year ago because it's finished its observations. It operated for 15 years. And it measured, again, millimeter wavelengths, but at 5 different wavelengths. This is now pitched in a gigahertz in frequency units. And its key sort of defining factor is it's got 5 times the resolution of the Planck satellite and about 3 times lower noise. So those are the 2 things where you can gain and learn more. And we're currently analysing the final 5 years of its data that we took up to 2022. And it's a big collaboration of now about 200 people, led by Suzanne Staggs and Mark Devlin. And this is a picture of some of our team members here.
Which part of angular scale corresponds to
so we measure to arc minute angular scale. So we get the resolution that we see to is 1 arc minute on the sky.
So it will be the region where the Planck
it's out, and okay, so yeah, very good, I'll show you. So we basically measure out to much smaller, to a higher L, so smaller scales than Planck. We don't measure the very, very largest scales. I sort of show you, it's kind of a neat complementarity. Planck will still be very useful going forward because it's measured the large scales, and we can't see those from the ground well because the atmosphere messes up our measurement of that. And so what you do is you use the large scales from Planck, and then you move the small scales from ACT. Out to L of 10,000, it goes. Let me orient you on the sky where we were able to see. So this is I've now flipped the coordinates into right ascension and declination equatorial coordinates, where this is the CMB map from Planck. We've left the galaxy in, so the galaxy is doing this in these coordinates, right? That's the Milky Way mission. And then visualized over here is the sky that we see from ACT. With ACT, and the map is a combination of the 2, just so you can sort of see it all clearly. You can't see at this resolution how ACT adds to it. I'll show you in a minute more how it adds. But this is the sky sort of footprint of where we observe. And so you see it's nearly half, it's almost half the sky, which is also kind of really useful for overlap with optical surveys and combinations with them. Okay. So let me show. So what I'm zooming in here is just a visualization of how the resolution shows up in the CMB blobs. Right, we're used to seeing the big Planck map with its blobs. I'm now zooming in. This is still the Planck data here at 2 millimeters. Each of these squares is a degree on the sky, so kind of a thumb's and arm length scale on the sky. And there you see the hot and cold fluctuations from CMB. And if you add ACT, then you see, I'll go back and forth, the fluctuations come in better focus. This is just the temperature. So if I go back to Planck, you lose some of the resolution and you bring it in with ACT. And what pops up as well are all these like red spots. And those are actually AGN. So these are AGN that are emitting in this wavelength. You get about 1 per square degree. It's pretty cool because we've got half the sky, so now we have a sample of like 20,000 AGN. You can also measure their flux as a function of time and start getting light curves. So a kind of side result of these data are kind of variable AGN studies, which we never really planned to do with this telescope.
Do you know the redshift of the AGN?
They are going to be really broad actually distributions. So 1, 2 redshift.
That you can you
No, we can't tell. No, but they've mostly got matches in known catalogs.
Oh,
Yeah.
I see.
So they match. So they're not a new sample of AGN, but they are be able to track their light curves with time. Also new measurements of this wavelength as well. Active galactic nuclei. Sorry, thank you for asking. So this is yeah.
I thought I was the only one who doesn't.
No, sorry. So imagine a very bright, a super bright imagine a supermassive black hole has pulled an accretion disk around it and is emitting in the radio and sending out radio emission from
Do you
Form
know?
of active matter, sure, so you should know.
Did you know? Did they ever search? Did anyone search for true transients,
Yeah,
like
we
fast
found that.
radio bursts and things?
Yeah, we did. Okay, we didn't with ACT yet. We've only found. I mean, only they're still nice, but they're not extragalactic. We found the transits we found are flaring stars.
I see.
Yeah, and so we think that we'll need the next generation SO to find the first not extragalactic ones. Yeah. Okay, so yeah.
Oh, yeah. Should I be surprised that it looks like you're finding AGN in both hotspots and cold spots?
They are. They're completely uncorrelated with it. They are just in front.
Oh, I see. It's
Yeah, so
over.
they are. Yeah, so think of these as a foreground, right? The thing that you do. Sorry, these blue spots are actually galaxy clusters, though, which the CMB has scattered through and scattered the light. So we do actually get to see galaxy clusters that way. But yeah, the red spots are just in front of the CMB. Okay, so how have we used this already, I think, to weigh in on that second curiosity, which is, are cosmic structures less enhanced than they're supposed to be if Lambda CDM is correct? Because again, that would tell us that there was something wrong. So how have we been doing that? So what do we think cosmic structures look like, or what is the structure of matter in the universe if we could see all of it? So if we could see the dark matter, which is again 25 times more plentiful than the regular matter, this is just one simulation of what we think the dark matter looks like. So where you see the orange light, the yellow light, that tracks where this is a computer simulation output that tells us where we think dark matter is clustered. So there's more dark matter where it's yellow and less dark matter in these voids where it's purple. And so that computer simulation says that if we could only see the universe with our dark matter eyes, right, we would see this kind of structure underneath. And when we go and look at galaxies, the galaxies that we do see are sort of sitting on this cosmic web. They're tracing it themselves, that where there's overdensities of the dark matter, we also will find galaxies. And so if we talk about sort of the clumpiness of the universe, if we made it less clumpy, we'd imagine like washing out the enhancement of this cosmic web, making the sort of this is like a peak of dark matter. We'd make it less peaked and the voids less voidy, right? You kind of reduce the contrast, the extremities of this structure of this cosmic web. And so our goal is.
That you like corresponds with cannot be defined with the parsec, but
I'm sorry, yeah, so megaparsec is 1 million parsecs, so about 3 million light years. Sorry.
but where eight is what?
The Hubble constant. I'm sorry. So here, yeah. So this would be divided by 100. So this would be like 0.7. So this would be just astronomy units. So this would be this would be 100 divided by 0.7.
Excuse me, a question.
Yeah.
You mentioned before about power law distribution of gases. So here you're talking about violation of this power law or about some features of the power law?
Very good. So what we're seeing here is not the power law just evolved to the CMB, it's evolved all the way through to today when structures have collapsed, so things have become nonlinear. So at this point, the power law is not there. The power law has sourced this, but it's been overtaken by gravitational collapse. So the gravitational collapse will form these structures. Yeah.
For this simulation, do you assume that dark matter has any other interactions besides gravity?
No, and that's an excellent question. And so a number of people, and probably Neil and others, certainly our colleague Mariangela Santi and others are doing, probably Ken, are doing simulations of what this looks like in an interacting dark matter, and seeing how this changes, seeing how the statistics of this change.
If you only have gravity, how do you get clumpiness?
You're saying just the gravitational collapse when I'm saying, so maybe clumping is the wrong word, I'm saying how extreme are the overdensities versus the underdensities here? So maybe that's the wrong way of saying it. But I'm just saying how enhanced are the voids and the peaks of the matter distribution. Okay, so how do we go measure it? If we can't, we'd love just to be able to look at it and say, what does it look like? But we can't do that because it's invisible. And so one of our key tools is to use gravitational lensing. So you use a backlight to see how the light bends around the invisible matter. Like the cartoon shows, if I'm trying to measure this thing, then my light will bend around it. And we've used to this, we've seen this more beautifully visually with JWST, where you see in optical light, these galaxies have been distorted gravitationally, this is strong lensing, by being distorted by a mass that they're being lensed around as the light comes to you. So the galaxies themselves get smeared out because their light gets distorted around a mass as they travel to us. It's like the cartoon here, right? You've got the rays of light, something bending around them. But we actually can use that exact same effect in the CMB. This is an extreme cartoon. It's more, the CMB doesn't, sadly, it's not this extreme for real, of what the CMB would look like if you put a giant mass in front of it and you say, what would you see? The CMB light would get coherently bent around this giant mass on its path to you, and you'd see it distorted like that, right? Now it's not the real distortion is much less, but we can use this feature to actually take the new map of the CMB and figure out what was the mass that did the distorting. And this is this new map we have from ACT this year, that the new map is the purple and orange part, the black and white is a lovely image of the dust that we're looking through, the Milky Way that we're looking through to beyond. And this was a map made, just this year from the ACT data from the whole team, but with, I must call out Frank Chu, Madhava Cheryl, and Blake Sherwin led this work, the collaboration. Okay, what are you seeing here? This is basically a map, the orange and purple part, of the integrated dark matter, or really all the integrated matter, most of it's dark. From here out to the CMB, it's saying in any given direction, how much did the CMB get bent, and therefore how much mass was along that line of sight. And so where you see it be orange, there's more mass in that direction on the sky, on average, all the way through the universe in that direction. And where you see it be purple, there's less mass in that direction, all the way through the universe. And again, say all the way through the universe just means what's the average mass along that sight line. This is now high signal to noise. It looks kind of like speckledy, and you might think, oh, it's just noisy. It's not noisy. This is high signal to noise measurement of these fluctuations. And the scale is about a degree scale on the sky again, and it's measuring dark matter fluctuations of length scale of hundreds of millions of light years. So think of these fluctuations as very long wavelengths at that particular scale on the sky. And so how featureful that is a measure of how clustered the universe has become. You know, if you imagine if you had no contrast today, you would have no, you know, there would be much less difference between the yellow and the purple. So let me, so what am I showing you here? I'm doing the same trick of taking that new image and again, taking its power spectrum. So decomposing it as a function of scale in the sky and computing the variance in that image as a function of scale. And so this is the power in that map as a function of angular scale, where this is degree scale in the sky. And this whole range covers kind of like 30 to 300 million light year scales on the sky, and breaking it down from the larger scales to the smaller scales covers this range of length scales. The data points here from that map are in red, like this. And this is actually a case where the fit here, the curve here, the black curve is now is a prediction. Okay, this is not fit to that data. It is the prediction of the Lambda CDM model that was originally fit to the early universe CMB data. So this is like the sort of concordance Lambda CDM model. And it's like it's a beautiful fit. Okay, so it really goes, we actually don't fit it in these blue ranges because there's some worry about potential foreground contamination. So it's actually fit in this central range. And if we were to say, you know, what would ideally this amplitude want to be, it would be only 1% higher than 1 is the prediction of the standard Lambda CDM model. So what are we learning here? We are learning that like the measurement agrees perfectly with the Lambda CDM prediction. Like this new data, which is specific sort of data, say that on the scales that we can see, there is no sign of cosmic structures being suppressed, because if the cosmic structures were being suppressed, we would see that red curve being below the prediction, come out below, but it's not below, it's bang on.
Is that 1% being driven by that data point?
I don't think, yeah, I mean, the error bar is 2%, so yeah, it probably is a little bit that one would pull it up a bit, but the error bar is 2%, so it's really not, it's truly consistent with 1.
So it's effectively the effect of dark matter.
This is what this is saying if I take it, is basically almost all of the signal is coming from dark matter, because the majority of that mass map is mass from dark matter. So this is saying what is the kind of what is the clumpiness, exactly. Yeah, exactly. That's right. I will say as well, because I think this is one thing I'm super excited about in the future, is that these same data actually provide, coupled with data from Sloan and from Sloan data, and equivalent to Planck, the tightest current limits on the neutrino mass sum, to say that in passing, give a whole talk on that. If you had a higher neutrino mass, you would actually suppress some of this power at the sort of smaller scale, the smaller side scales of this, but that would be an extra parameter in your model. So
can these ground-based ones eventually do as well as these S4s?
So S4 is going to be, so the program of this is that for the next, just finished, for the next 10 years, we'll actually have the Simons Observatory. And then the next 10 years, we'd have CMBS4. So CMBS4 would be a decade from now. And so if we think about the program of measuring this better and better and getting towards neutrino mass sort of detection, it'll be a refinement of this coupled with like DESI measurements of galaxy clustering. The combination of this plus the improvement of this should hopefully get us to actually seeing neutrino mass.
So, and then improvement is
So exactly, yes, exactly, factor 4. It will come partly from this, and then also from the DESI. Yeah.
So how much will S4 contribute?
Oh, S4, by then, this is separate discussion. So S4 will actually only be able to improve the neutrino mass if we can make a better measurement of the optical depth to realization, because they're degenerate. So actually to make progress much beyond the next we'll kind of continue making progress, and then we'll hit a plateau where if you don't measure the optical depth to realization, you actually won't do much better. Yeah. Sorry, I'm going too slowly. I'm just going to comment on this so I can go on past. Is that not only there's one sort of feature of this measurement, which is that it picks up most of its information actually when the universe was half its current age, because lensing of light, just the same as optics, right, is most sensitive to stuff that's half the distance between you and the source. And so it's a weighted mean of all the matter along the line of sight to the CMB, but it's mostly picking up stuff halfway in between us and the CMB. But since this measurement, we've also taken that map and correlated it with galaxies that are closer by, such that you only pick up the bit of that signal that's nearer by. And we see basically exactly the same consistency. We see the same consistency at closer by. I'll just show this here quickly too, that this is sort of the relative amplitude of the clustering compared to Lambda CDM. And this is at half the age of the universe and then closer by points as well. And it's still consistent with one, which says that there's no problem with Lambda CDM here. But the important thing to say here, though, I think, is that what we have shown from this is that this potential problem of there being not enough clumpiness or clustering of matter in the universe doesn't appear to be a large-scale effect. All the way sort of throughout the universe, it seems to be no suppression on the large scales. But we don't probe with our data things that are larger than about 0.3 or 0.4 inverse megaparsec. So again, a megaparsec is 3 million light years. And so the originals, the lensing of galaxies actually probes even smaller scales, smaller separations. And that's the data that appears to be a bit suppressed. So it feels like we've narrowed down the place where the problem might be, which is that it's at small scales. It doesn't seem to be at large scales. So there may still be this suppression again, but it's probably limited to small scales. And that's interesting because sort of either it's new physics at small scales, it could be dark matter that's behaving unusually at fine scales, or something else. Or it could just be that we have misunderstood the feedback effects of baryons that could also affect the observations of those scales. I think that's possible too. Okay, so I'm just thinking I went too slowly. So let me just come to where we're going to with curiosity number one. That was curiosity number two, which was the clustering. Is what about the Hubble constant? Is the universe expanding too fast? Faster than Lambda CDM predicts? And so, again, this is a summary of like the expansion rate of the universe, measured as a function of time recently over the past 20 years or so. And the measurement of the CMB is coming down here and come down to this prediction in Lambda CDM of a lower value that has been measured by a couple of different methods of measuring galaxies directly. And it's occupying the community extensively. We call it the Hubble tension. Why is this one? This prediction of Lambda CDM, why is it lower than what's been measured from? There's been more history of this Cepheid measurement of pulsating stars, calibrating distances, and there's also a new measurement coming, but it's higher but not significantly.
Excuse me.
Yeah.
What about the measurement of H0 by lensing, like Holy Cow?
Ah, yeah, no, very nice. Yeah, no, I didn't put it on here. So the Holy Cow, their measurement has large enough uncertainties that it captures them both. It's super interesting, but it's consistent with them both. Yeah, so it's a very nice progress, but it could be consistent with here. So we are able to measure. Why do we measure the Hubble constant at all with the CMB? It basically scales the distance to the CMB. If you increase the Hubble constant today, you say the expansion rate is faster. then you decrease the time since the CMB set off. Because what you have to do is expand the universe by a factor of 1,000 in all directions. And so if you're expanding faster today, then that happened in less time. So the CMB is closer to you. And if the CMB is closer to you, all the angles go to shift to larger angles, right? You go closer to something, you get a larger angle. And so if you increase the Hubble constant, you shift all of the peaks of the power spectrum to larger angles. And so we get to, that's why we can measure it within some model as the CMB. And so what we've been doing, so imagine that, again, this is a sort of a snapshot of this, again, this power spectrum of the original maps is up at the top there is these acoustic peaks in the temperature. And actually down below is when you take a decomposition of the polarization signal, we get acoustic peaks in there as well. And every time you get an acoustic peak, you're actually making a measurement of the angle to the CMB. Every single peak is another measurement of basically the angle to the CMB. And so you shift that back and you can shift that back and forth and change the Hubble constant. So this was a measurement we made a few years ago, but we've been intensely analyzing our data ever since. And what we're trying to do now is make a much better measurement of this lower curve, which is the polarization power spectrum. And I just want to show you quickly before I stop. That this is a little cartoon of how much higher sensitivity we have. Just let's look at the top panel. The top panel is fluctuations in the size of the polarization signal of the CMB, measured in ACT versus Planck. And the Planck on the right is basically noise dominated. What you're seeing is very noisy. On the left, you're seeing being revealed by ACT with much higher signal to noise. You're seeing those fluctuations now pop up with really high signal to noise. And it's the power spectrum of these that we are going to be using to test for models that depart from Lambda CDM. So test any model you come up with that might try and increase the Hubble constant, be it by like including like a new dark energy component or interacting neutrinos or anything that you can do in the early universe that you can think of that might possibly increase the Hubble constant in the universe. We're going to be able to look at the, this enhanced measurement of the CMB with these new maps and test those. So we are currently pretty far through this analysis, but we haven't quite looked at our cosmology results, and we hope to do so pretty soon. And they will go further than Planck, particularly in polarization, as you see from the noise improvement.
So you have models in mind that you're testing?
Yeah, so what we're going to do, we're going to test a bunch of models, and then we're going to make all the data public so that you can all test models too. So the models that we'll be looking at are things like interacting neutrinos, early dark energy, a bunch of other possible models, but we're actually hoping that the community go and test more. We'll do some. Yeah. All of those ones would show up looking a little bit different. And then just finally, we will then move on past that to the Simons Observatory. So ACT was here, it's been taken away, and next to it has been built this array of new telescopes, which is the Simons Observatory, including one large telescope here, which is taking over from ACT. It's got more detectors, so it's more sensitive. And it's also got 3 smaller telescopes that are going to be looking for a gravitational wave signature from the early universe. It's commissioning right now, and then it will run for 10 years. You can see up close, it's not fully commissioning because this big telescope hasn't yet got its mirrors in, but the small telescopes are commissioning. And the timeline of it is it would run basically all the way through till the early 2030s, and then CMBS4 that would start around then. So I will conclude. So yeah, we would love to see something that departs from Lambda CDM. We've already learned, I think, from new data that on large scales, cosmic structures really are behaving as expected. We'll see what they have to say about the Hubble tension. And I will just say it's been really fun to use millimeter wave data for all sorts of other things like transients, searching for Planet 9, all sorts of things we weren't ever expecting to do. And the data will be public soon enough for people to do more stuff with it.
there prospects for measuring temperature fluctuations at large scales, larger than 10 degrees?
Yeah, you need a satellite for that. And so, I mean, at large scales in temperature, Planck has done it. So WMAP did it too. So we've now got 2 measurements there, cosmic variance limited. We can't do any better in temperature at large scales, but in polarization, for sure, we could do better. The nearest term prospects are there's a Japanese-led satellite called Lightbird that hopes to measure the very largest scales, not to very high resolution because we have the ground-based data, and that would hopefully, if it gets launched, kind of late 2020s, 2030-ish. Euclid is beautiful, but it will do optical measurements. So it will measure galaxies and galaxy lensing. And so it will measure the dark matter distribution via its methods of the lensing of galaxies. So it'll be extremely interesting to see how those maps of the dark matter compare and be combined with our ones from the CMB as well. So yeah, that's very exciting.
On large scales, what makes it hard to measure the polarization? Is it just atmospheric effects?
Yeah,
it's not foregrounds. It's atmospheric problems, not foregrounds.
More so, we are limited on the ground from atmospheric issues, yeah, rather than foregrounds. Yeah, but it is true that.
And you don't think that's surmountable? You think you're done? You have to go to space.
Okay, so the CLASS telescope, which is just on the same site as us, actually led by Chuck Bennett, they are seeing how low they can go. Mm-hmm. They're trying to get to like L of 10. Mm-hmm. And if they can, that's pretty interesting. And so I think they are exploring what you can do with like spinning around a lot and trying to separate out the signal. And I think we'll learn from them in these next few years, like, yeah, again, how low can you go? We should try, if you can, we should try it.
Sure. I'm still thinking about this clumpiness of density.
Yes.
And you are describing this lensing effect from the clumps like apple of some sort. But the picture that you showed, and also my obsolete ideas about how gravitation should work, these clamps should be connected by lines, and it should be like a network. So how does network?
Very good. Okay, I'm slightly trying to illustrate something with something that's slightly different. So what I will say is that with the CMB lensing at least, we're actually measuring, as I said, we're measuring sort of fluctuations on hundreds of millions of light years scales. So on that scale, on those scales, we're still actually measuring the linear. We're still measure linear fluctuations. We're actually not trying to measure lensing zoomed in on a sort of cosmic filament that's highly collapsed.
What would be the length scale of this network?
Oh, of these filaments, they would be sort of so the typical separation of a galaxy is about a megaparsec, about 3 million light years. And so they would be filaments sort of connecting galaxies on those kind of scales, like maybe a bit more, but.
So it's comparable to the intergalactic scale.
It's basically it would be, yes, but it would be, and the key thing here is that it would be on and not in the scales of like non-linear collapse. And so actually the measurement I showed you actually is on much larger scales where we're still thinking more about just the large scale fluctuations. But people are also doing measurements that look down to small scales. It's just not what our measurement was.
Other questions?
One, I'm gonna say that you kind of can predict what I'm about to say, but that you're asking, you want Lambda CDM to be wrong, and I do too. But I believe, my feeling of why it's wrong is because the assumptions that were written down for Lambda CDM were fundamentally written down to make the system easy to calculate. In the 80s, Dickey's group was asking, what things can we calculate in this situation? And they said, well, if we assume things are adiabatic, and assume it's a Gaussian, and assume that there's only a few components, and assume it's in thermal equilibrium at early times, we can calculate some things. And then that model, which really was written down for simplicity, I just want to know if you have any reaction to that situation. Because to me, that it should not be a cosmological principle that the model that's easiest for cosmologists to compute is the model that's most likely to be correct.
Yeah, it's weird. I mean, I think when, you know, and I think when I hear, I'm sure you do too, you know, Jim Peebles talking about this, came up with it, I think he thinks it's pretty surprising too, you know, that it keeps working, and it's, yeah, why should it be that one? I mean, of course, simple to write down means that it hasn't got as many details as something that's more complicated, but I do find it weird.
I think one thing that the Hubble tension did though was force people to like reevaluate all those assumptions and like, you know, try to vary them to see could you match it. And so we know even better that the simple assumption, I mean, it's not all published, right? Because there's lots of models that just didn't work. But at this point, like we did, lots of people tried lots of stuff.
Right, and it shows that that anomalies are very productive. Like sometimes people make fun of us like pursuing anomalies, but actually anomalies are super productive because they force people to reevaluate everything.
Yeah, I agree.
I mean, it would also be productive to write papers on things that didn't work sometimes, so people don't.
That's true.
All right, on that note, writing wrong papers.